The task in this problem is to calculate the load impedance for maximum power transfer to the load in this circuit. The maximum power theorem, when applied to AC circuits, states that the maximum power will be delivered to a load when the load ZL in this case is the complex conjugate of the Thevenin impedance across its terminals. Applying Thevenin's theorem to the circuit, we first remove the voltage source by replacing it with a short, and the Thevenin impedance ZTH is the parallel combination of Z1 and Z2. Mathematically, this is Z1 times Z2 all over the quantity Z1 plus Z2. Plugging in our values, we get 10 at 53 degrees times 8 at 90 degrees divided by 6 minus J8 plus J8. Z1 and Z2 are given in both polar and rectangular coordinate values, which, after reducing the fraction, we get 13.3 at 37 degree ohms in polar coordinate format, or in rectangular coordinate format, it is 10.6 plus J8 ohms. The Thevenin voltage is the voltage measured across the points where the load is to be connected. In this case, it's the voltage drop across Z2, which, using voltage division, gives us E times Z2 all over the quantity Z1 plus Z2. Plugging in our actual values, we get this. And ultimately, we end up with 12 volts at 90 degrees. Our Thevenin's circuit, which looks like this. Remember that in order to draw maximum power, the load impedance must equal the conjugate of the Thevenin impedance, which is 13.3 at minus 37 degrees, or 10.6 minus J8 in rectangular coordinates format. The load impedance is made up of two parts. One, the real part, which we call RL, and that's equal to 10.6 ohms, and the imaginary part, which we will call XL, and that's equal to minus J8 ohms. Since we are looking for the real maximum power delivered to the load, we only have to consider the resistance RL part of the circuit because it is the only part of the impedance that dissipates real power. The maximum power that our supply can deliver to the circuit is given by the square of the source voltage magnitude all over the circuit resistance, E squared all over R. In order to find the maximum power that our supply can deliver to the load, we now use the voltage division rule, giving us the square of 1/2 the source voltage magnitude, because the load resistance and Thevenin resistance are equal, all over the load resistance, which is given by the square of the source voltage magnitude all over 4 times the load resistance, or 12 squared divided by 4 times 10.6, which works out to 3.4 watts. It's interesting to note here that the maximum power that can be delivered from a circuit happens when the load resistance is equal to the internal resistance of the supply, or when dealing with impedances values, the maximum draw from the source is given by the load, which is the conjugate of the internal impedance. In this case, the internal impedance of the source is the Thevenin impedance. The fact that the load is the conjugate of the source impedance means that the reactive current is going to oscillate between the impedance of the load and the internal impedance of the source, similar to what we have seen in our last problem. And the current delivered to the circuit is going to be at 0 degrees, or considered a real value. In recent years, the reality of climate change has become impossible to ignore. Severe weather events, floods, tornadoes, violent storms are growing more frequent and more intense. For homeowners, this means that the utility power outages are no longer a rare inconvenience. They can last for hours, days, or in extreme cases even longer. The question is no longer if, but when you'll need a solution to keep your home powered and your family safe. When it comes to residential power backup, 𝐃𝐈𝐒𝐂 offers a range of solutions suitable for everything from powering a single appliance during a short outage to running an entire home in the event of an extended blackout. You can have a look at all of these options that are available by simply going to this web address.